right, so hopefully that video was helpful for you to see pressure. As you increase the amount of surface area, it takes a greater amount of pressure to still pop the balloon. I want to now talk about the liquid force that is exerted. We talked about that there is force, right? We said that the force is normal to every surface. We said that there is this force even when the liquid's not moving. But how much force is there? So in your notes, for a container of liquid, maybe that's a kiddie pool, maybe that's a glass of water, whatever it is. For a container of liquid, we understand that there is, however, a force that bears down on the bottom of the container specifically. There's force everywhere. There's normal force perpendicular to every surface, but there's also force downward. How much force? Well, does it make sense that the more liquid there is, the more force there will be? For instance, if you've, any of you try to go down to the bottom of the swimming pool and grab things off the bottom or whatever, and you know that as you go down deeper and deeper, right, you feel more and more force bearing down on top of you, right? Well, you're going to get more force if there's more liquid, because literally what's bearing down is simply the weight of the water is on top of you. So the force that bears down is a force of weight in a sense. Don't write this down yet. I'll tell you what to write down next. Well, what is weight? How is weight defined, Audrey?
The pull of gravity on an object.
The pull of gravity on an object's mass, right? If gravity becomes stronger, you get more weight, or if mass increases, you get more weight. Because it depends on those two things, really, this force is simply the product of mass and gravity. But think about what mass is. The mass of an object depends on its density as well, doesn't it? Right? For instance, we could get different people all Michael's size, but if they have differing, they all have the same, if they're all Michael's size, but maybe one guy is like, it's all flab, and another guy, it's all muscle, but they're all the same size as Michael, right? That's going to change the mass as well. We know that density is mass per unit volume, so therefore mass is the product of density and volume, correct? You follow? So weight then could be defined as the density of the liquid in question times the volume of liquid times gravity. Does that make sense? So however much gravity is pulling on the liquid, obviously if there were no gravity, the liquid just sort of floats away and there's nothing bearing down on you at the bottom of the pool. The volume, the amount of liquid that's pushing down on top of you, and the density of the liquid you're in. For instance, again, it would kill you, but mercury, right? So if you were swimming in mercury, okay, there's a much greater density to mercury, right? So it would crush you very quickly. Well, think about what volume is. Remember back in your junior high days, we said for a box, the volume was the length, the width, and the height, right? We said if we had a cylinder, for instance, it was the 2 pi r, or the circumference down here, times the height, right? In fact, we said really for any prism, maybe it was a triangular prism, and that should be dotted, but anyway, for a triangular prism, you'd have to get the area of the bottom times the height. So volume then loosely could be defined as cross-sectional area of whatever this container is times height. And if we take all these ideas and put them together, we get the equation I want you to write down finally. And that is the force that a liquid presses down with, the number of newtons it pushes down with, is equal to the cross-sectional area upon which the liquid is pushing, times the density, times the pull of gravity, times the height of the liquid, or when you're at the bottom of the pool, the depth of the liquid, right? The height of liquid on top of you, or from above perspective, is the depth of the liquid. And there's our first big equation. We have two equations, right? Pressure equals force over area. That was our first equation for this chapter. Second formula for the chapter is the formula for force exerted by a liquid on the bottom of a container. F equals A rho GH. Where again, A class is cross-sectional area. That's going to be in square meters. Rho is density, right? It's going to be, and for this unit, we're going to go with kilograms per cubic meter instead of grams per cubic centimeter. G, that's gravity. We're going to assume, by the way, if you'll note this, we're going to assume gravity to be 9.80 meters per second squared. Now, it will change depending on where you are on the Earth. But for our purposes, unless a problem states otherwise, we're going to go with this number here. That's kind of the average number on Earth, okay? Some textbooks you'll use will go 9.81 because here in the United States, most places in the US, it's 9.81. That's to the hundredths place anyway. Yeah, we're more global than that. So 9.80 meters per second squared is what we're going to use in this class. And then the height refers to the depth. That's going to be simply in meters. Notice how the units play out. These two meters and meters squared, would cancel with the meters cubed, leaving us with kilograms times meters per second squared, which is newtons. So that's how the units are going to play out. Oftentimes, we'll be using pure water or assuming pure water for our liquid. If we have water, from your homework reading, that number is going to be 1,000 kilograms per cubic meters. So if we're going with water as our substance in question, we're going to say 1,000 kilograms per cubic meter. Obviously different, depending on what's in the water could change that number. Salt water, seawater obviously is going to have a little higher density than that, but unless it specifies otherwise, we're going to assume 1,000 kilograms per cubic meter. We'll just assume pure water, even though everyone knows there's chlorine in it if it's in the pool, or the pool salt, which turns into chlorine. Anyway, I digress. Well, let's take now the two equations we've talked about, though. Because force, how much force bears down upon you, is different than technically the pressure that bears down upon you, right? Because after all, you don't cover the entire bottom of the swimming pool. And it would be really hard to calculate your square meter area of how much you take up, right? So for our purposes, we'll also look at this idea of pressure. Pressure takes force, which is A rho GH, and divides the area out. So pressure then is the same thing as force, but with the A divided out. And so pressure is simply rho GH. We call this the law of liquid pressure. The law of liquid pressure. P equals rho GH. Again, the rho is the density, which if it's water, we're going to assume 1,000 kilograms per cubic meter. The G is the gravity, which again, we're going to assume, class,
9.0 meters per second squared.
thank you, Audrey. Class, we're going to assume G to be
9.80 meters per second squared.
good, and then the height, of course, would just be in meters. Again, it's called the law of liquid pressure. And this takes the need to calculate how much, what your square meter surface area happens to be. Pressure doesn't have to account for the area at that point. Look at page 36, if you would, please, with me. Page 36. And let's work just a couple of math problems with these before we wrap up. Page 36, example 3.1. Michael, if you'll read part A for us.
If the density of water is 1,000 kilograms per meter cubed, what is the pressure at the bottom of the pool filled to the depth of 2.4 meters?
All right, it says, what is the pressure? All right, well, if we're finding pressure, class, what formula do we use? Well, we could either use force over area. Does it tell me a force? No. Does it tell me an area? Let's not use that one. Okay, so what's the other equation I could use for pressure, since we're talking about a liquid, so we might use liquid pressure? Okay, we're awfully quiet. Wake up. What's my formula for liquid pressure, class?
P equals rho GH.
P equals rho GH. And so we want to find how much pressure, by the way, remember pressure measured in pascals, how much pressure is there going to be at any point at a depth of 2.4 meters? What's that pressure going to be at any point along the bottom? Well, in for the rho, that's density, class, we're going to plug in
1,000 kilograms per cubic meter.
All right, thank you, Audrey. Somebody besides Audrey, what are we going to plug in for the G?
9.80.
Good, 9.80 meters per second squared. That's the acceleration due to gravity. And then for the H, what are we going to plug in, Michael?
2.40.
2.40 meters. All right, so there we've got our three numbers, and it's just pretty easy. You multiply the numbers together. So go and do that at your seats. Multiply all three numbers. You're going to get a really big number. A Pascal is a relatively small unit, okay? So you should expect a large number. How many pascals of pressure, your class?
1,000 up to 20.
I got 23,520, but sig figs. What are we going to round to? Well, the 1,000, if it's pure water, is exact, so we're not going to use that for sig figs. We'll go off one of these two. Again, generally, we're going to look at numbers given in the text. So we'll roll with the 2.40 telling me 3 sig figs. Let's round our answer off to what?
23,500.
23,500 pascals. You could say 23.5 kilopascals or 2.35 E4 pascals, but I just didn't go with that one because I'm lazy. All right, questions on that? Look at part B. Go and read that for us if you would, Kendall.
What is the total force in newtons on the bottom if it is 5.50 meters wide and 10.0 meters long?
Good. Okay, so they give me the actual dimensions of the pool here. 5.5 meters wide, 10 meters long. And they want the force on the bottom, okay? In general, what's my equation for force on the bottom, class? Okay, thank you, Audrey. Class, what's the equation for force on the bottom of a container? F equals A, rho g. So let's try it in unison this time. Class, what's the equation for force on the bottom of a container? Good, but we understand the rho gh part we already found, didn't we? So we want to be lazy, because I do. We could extrapolate this, that force is equal to area times pressure, since after all, this is the pressure anyway. So we just need to multiply the area by the pressure that's already on the calculator. Well, we could do the area in our head, right? Area is length times width. Apparently it's a rectangular pool. 5.5 by 10 is how many square feet of area? 5.5 by 10. 55, right? Multiply by 10 to the decimal. So we really just need to take 55, stay with me, square meters, multiply that by the pressure, not the rounded number, by the way, the exact number, and we multiply. And we get, ooh, lots of newtons.
1,293,600.
And again, 3 sig figs, so we'll say 1,290,000 newtons. Or here's a good time where maybe we do want to use scientific notation. Let me show you how to do that real quick. Do you still have the number on your calculator? All right. For those who have a calculator like mine, the TI-30XA, do you see right above the 5, it says SCI? That's how you put something in scientific notation. Now you're going to need the second function button and then the 5 button. So second function, SCI, and it'll actually give you, notice, 1.2936, and it'll give you a little 0.6. That's your E value. So 1.293 sig figs, E6 newtons. So if you get a really big number, you put it in scientific notation. Michael, your calculator's a little different. I'll look at that with you right after class. Questions on this? All right, we'll pick up with this more tomorrow. No homework this evening. Have a wonderful rest of your day. You are dismissed.